This lecture is about objects in Scala programming. Previously, we learned two ways of declaring variables using val and def. And val corresponds to eager evaluation or call by value style, and def corresponds to lazy evaluation or call by name or textual substitution. There's yet another way of declaring variable, which is lazy val. Lazy val uses this lazy evaluation, but unlike def, it is based on call by need. Here's an example. We declare variable x using lazy val, and at the time of declaring this variable x, nothing is computed because it is based on lazy evaluation. The first time we access this variable x, we actually evaluated the expression, and therefore this print line is executed. So we print this line, and after the expression is computed, we cache the result in memory. So the result is 20, so we allocate the memory cell for x and then cache the result. The next time we dereference variable x, we just retrieve the value previously cached. So this time, this print line is not executed, and we don't see the same message again here. So this is the way call by need works in Scala programming. This is an actual example of using lazy val. You can see that this expression is not trivial to compute, and it may take a while to finish the computation. And moreover, this variable may not be used at all. So if a variable x takes a while to initialize, and also if this variable x may not be used at all, you can actually choose to use lazy val. But there's also a downside in lazy val. In the actual implementation of lazy val, there's a lot of overhead, and we will come back to this issue later. A distinctive feature of a Scala language is it allows only one constructor per class. For example, in this class, rational, you can have only one constructor with two arguments of a type int. You can have multiple auxiliary constructors shown over here, which must be defined in terms of the existing primary constructor. So in principle, you can have only one constructor per class and multiple auxiliary constructors, which must be defined in terms of the primary constructor. The question is this good or bad? Is it a good idea to have only one constructor per class? It turns out that the Scala designer made a deliberate decision about the way constructors are provided to classes. After analyzing the practice in the Java community for 20 years, they came to the conclusion that having multiple constructors does actually more harm than good. So they decided to allow only one primary constructor for each class and allow multiple auxiliary constructors, which must be defined in terms of this primary constructor. Everybody knows the notion of a superclass, subclass, and base class. And we can have an abstract class, which is a class with methods that are not implemented yet. Here's an example of abstract class interset. This interset is abstract because the two methods here are left unimplemented. We can create a subclass of an existing class with the keyword extends. Here's an example of a concrete class, empty, which extends the abstract class interset. This class empty is concrete, and you can actually instantiate it to create concrete objects because all its methods are fully implemented. We learned that inheritance is a key feature in object-oriented programming. And the most important decision in object-oriented programming is when to introduce subclasses, and also what subclasses to create. These questions are important because it's really bad practice, it's really bad idea to create many classes in your program. For example, you can have a superclass, you can have a subclass, you can have subclasses of a subclass. And having this many subclasses is actually complicated the reasoning about your program. And eventually, your program with lots of classes will collapse under its own weight. So we have to be very careful about when we decided to introduce subclasses. And we have to be careful about what subclasses to create. So here's an example. In this example, we are implementing a class interset. We start with this abstract class. And in this particular implementation, we decided to create two subclasses, empty and non-empty. And the question is, what is the principle behind making the decision to create the subclass empty and non-empty? You can have your own solution, and for the problem of implementing interset, every student will bring his own solution. So what is the guiding principle? What is the rationale behind this decision of choosing empty and non-empty as subclasses of interset? What is the principle? So we should be able to answer this question ourselves. What kind of a principle, guideline, rationale do you employ when you decided to create the subclasses? This is a critical question to answer in object-oriented programming. Here's one particular principle that we can employ when we decided to create the subclasses. The answer comes from the abstract data types that we should be familiar from functional programming. Suppose that we want to define abstract data type interset in functional programming, for example, in OCaml. Then perhaps it is a no-brainer to create two data constructors, empty and non-empty. In other words, 9 out of 10, every student will bring this solution. And the previous code in Scala is based on this idea of defining abstract data type interset. Specifically, we translated the type interset into base class or trait, and we translate the two data constructors into individual subclasses. That's the way that we created these two subclasses for base class interset. In Scala, we have traits, which are similar to Java interfaces, but are much more powerful. For example, we have this programming technique called the stack of traits, which allows us to implement a design pattern called decorate patterns in a very elegant way. We will come back to the topic of design patterns later in this course. If we compare classes and traits, traits are much more flexible to use. For example, suppose that you have only classes. A class can have only one superclass, so now it is very hard to express different properties for different classes. But with the traits, it's very easy to express different properties because you can just mix in different traits. Here are several examples. Here, we create a new class Fido by extending an existing class Foo. Here, we create a new trait Kido by extending an existing abstract class Bar. Here, we create a new class Middle by extending an existing trait Beam. In all these cases, we mix in two existing traits, hello and bye. As a result, all these three cases, class Fido, trait Kido, class Middle, inherited the properties expressed by this existing traits hello and bye. So it's very flexible. The remaining question is, when should we use abstract classes? And when should we use traits? Traits are similar to abstract classes in that they can have methods that are left unimplemented. And the answer to the question is, you should use traits instead of abstract classes in most cases. There's a slight performance penalty in using traits, but in practice, you can ignore the performance penalty. So you should prefer traits to abstract classes in your Scala programming. This is a Scala class hierarchy. In Java, we make a distinction between primitive types and objects. Examples of primitive types are int, float, boolean, and so on. For primitive types, we use native representation. For example, for an integer of a type int, you only allocate the 4 bytes. In comparison, for every object in Java starts with an overhead of 24 bytes. In Scala, we no longer make a distinction between primitive types and objects, at least semantically. So semantically, we have a single superclass at the root, which is Scala.any, and we have two major sub-hierarchies, Scala.anyFile and Scala.anyRef. And every class that belongs to any file uses native representation. So for example, Scala.int, although it is defined as a class, it consumes only 4 bytes in the representation, just like int in Java. In contrast, any object of a type anyRef, or its a subtype, consumes 24 bytes as an overhead, just like a Java object. And there are special classes, Scala.null, to represent null values, and nothing. And it turns out that this Scala nothing can be useful, and we will see why it's useful in the next slide. In Scala, we have a special class called nothing, and nothing represents a type that is uninhabited. This uninhabited means that the type has no value. For example, a type int has an infinite number of values, for example, 0, 1, 2, -1. So the type int is inhabited. But nothing is uninhabited, which means that there is no value of a type nothing. Nevertheless, nothing is useful in practice. For example, in Scala, nil, which represents an empty list, has a type list nothing. In Scala, you don't have nil for int list or nil for boolean, and so on. You just have a single nil of a type list nothing. And the way it works is that list nothing can be shown to be a subtype of list T for any type T, because list is defined as a covariant. What I mean by list being covariant is, if A is a subtype of B, list of A is defined to be subtype of list of B. So this is the property provided by the particular implementation of list. Because list is covariant, it suffices to provide a single nil of type list nothing to represent empty list for all types. If you are not familiar with the notion of a covariant and contravariant, you can read the course notes from the programming language course. Another example of using type nothing is to assign a type to an infinite loop. This infinite loop never returns and never produces any value, so it cannot have any interesting value because it never produces a value. So you can just assign type nothing to infinite loop and the compilation works. In this way, we can use nothing in practice for useful purposes. Let's look at the implementation of list of integers in Scala. In functional programming, in order to implement int list, you'd introduce this abstract data type with two data constructors, nil and cons. It's almost the standard solution. In Scala, you can have these two classes, cons and nil, implementing the same trait int list. This is the standard way of implementing list of integers in Scala programming. And it turns out that this example illustrates one of the key strengths of Scala programming, where you can have the best of both worlds, functional programming and object-oriented programming. To see why, in this style, you can implement abstract data types from functional programming, which is a really powerful abstraction available mostly in functional programming languages. But it also overcomes the unique weakness of functional programming. For example, in this definition of int list, you cannot have function f specialized for nil and the same function f specialized of cons, because in functional programming, you don't have this notion of method overriding. So you should have a single function f, which must take an argument of type int list, and then you should perform pattern matching here. That's the price that you have to pay in functional programming for using abstract data type. But in Scala, you can have specialized method in each of these subclasses. For example, cons has its own method contains, which is specialized for cons, and this class nil has its own method contains, which is specialized for nil. So therefore, in Scala, we have the best of both worlds. We can still use a programming style using abstract data types, but we can also use object-oriented programming. For example, by implementing contains method in each of these classes. It's hard to see why this is a powerful programming technique, but in my opinion, this is one of the key ideas in Scala-style programming, which mixes functional programming and object-oriented programming. In Scala, you can use type parameters. For example, in this definition of a trait list, you introduce type parameter t to represent the type of every element in the list. So the method head returns a value of type t, and tail returns list of type t. In this example, we define class counts which extends list of t. So the type parameter t is used for the type of head and tail, and also coincides with the type parameter used in list of t. And at the level of method, you can also use type parameter. For example, in this definition of a method singleton, you introduce type parameter t. With the type parameters, you can achieve parametric polymorphism or generics in Scala. Here's an example of defining a function pair which has a type parameter t and takes an argument of type t and returns a pair of type t. So its type is shown like this. It takes a while to get used to this form of a syntax, but basically what it says is its type is alpha dot alpha arrow alpha times alpha. So it takes a value of any type alpha, and then it returns a pair of values of a type alpha. And here we instantiated the type parameter t into integer, and this time the type inference is performed by Scala compiler. And in this example, we explicitly instantiated the type parameter t to type int by providing this type annotation.